In this video, we look at section 13.4, problem number 12, or a problem similar to problem number 12. So in problem number 12, you're given a curve r of t is equal to 6 sine of 2t, 6 cosine of 2t, and you're given the z entry as equal to 5t. Okay? So that's the curve you're given, and I would like to look at a curve r of t is equal to 2 cosine of 2t, 2 sine of 2t, and then I think I picked t for my z entry. So this is the book's example, and this is the example that I would like to talk about now. The example I picked is just easier when it comes to the plotting. The circle's not quite as big and all that. So you'll probably be asked, you will be asked in this problem to find t and n and then use that to find the curvature. Okay, so that's the problem you've been asked to compute. Okay, and I just want to point out something new to this problem is that your curve has three specific entries, three entries. So this is a curve in 3D. And notice that when we had the formulas t, which was r prime divided by magnitude of r prime, and n was equal to t prime divided by the magnitude of t prime, and then curvature was the normal component of acceleration divided by the velocity, the magnitude of the velocity squared, and normal component of acceleration was the acceleration dotted with the normal vector divided by v dotted with v. So this is the formula that we have. Nowhere in these formulas did we have to talk about being 2D specifically. You can also take 3D. These vectors, all these formulas just involve dot products, and we can take a dot product in 2D and 3D. Okay, so there are the formulas you're going to be asked to compute, and I just wanted to bring up this example over here. Here's the curve 2 cosine of t, 2 sine of t, similar to what I've given you, but it was two-dimensional, right? But as soon as you add a third entry, I mean, it's still a curve in three-dimensional space. Your vectors can still be defined, and your t vector is just the vector that is pointing tangent to the circle in this case. All right, so t can still be defined. You can still see your acceleration vector, and that's okay. Right? Now if you add on a z entry to be t, right, we haven't really affected the x and the y variables. We're still going to be a circle. Right? But if you look at your velocity vector and kind of zoom out on this thing, okay, let's just get a better view of this and increase the plot time. Okay. What we're seeing is that because we added on that z entry, now we're moving up. Z is changing. Okay, and if you look at it from the top, you're seeing a circle of radius 2, but because the z was getting bigger, we're moving up in what's called a helix. Right? So these vectors are defined in 3 dimensions as well as 2, so we can still do all of our tangential normal components of acceleration, right? And you can go through and figure out the computations. You can find your, here's your position vector, you can find your velocity vector, you can find your acceleration vector, and then do the acceleration decomposition problem, okay? So that's what we want to do. This is kind of just set up for the problem that we were looking at, okay? So let's move down to this example, and I will run it. This is an example that's like problem number 12, okay? And here we are seeing a plot. We're zooming out because now we have a circle of radius 2, and we were looking at a helix, okay? And you can see the thin red arrow is the tangential component. Okay, what we're seeing here is a plot of T and N. I got to zoom out a little bit more because T. So there's your helix, right? Thin red is your velocity vector, blue is the acceleration vector, and if you zoomed in, keep zooming in, then you can see T and N. Okay? And the acceleration for this helix seems to be pointing only in the normal direction. So we're expecting to see tangential and normal components. AT should be 0 and A sub n should be something. Okay, so what we're seeing here are the computations that you need to double check. Okay, you go through these computations and this is what you're working for. Here's your curve, x, y, and z. Velocity, the derivative of the first entry, derivative of cosine is negative sine, and then you get the chain rule, the derivative of 2t is 2, and that's where this minus 4 is coming from. So you compute the derivative of your curve, that gives you your velocity. Compute another derivative of your velocity and you will get your acceleration. There's a 0 here because of the 1 in the velocity. Now that you have your velocity, you can compute the velocity divided by its magnitude. And this is what you'll get. Okay, it looks like it's used a trig identity here. 2 sine cosine is the trig identity for sine of 2t, so it looks like the computer's used a trig identity. So this should be minus 4 sine of 2t. That would be equivalent. Okay, instead of minus 8 cosine sine, if you put minus 4 sine of 2t, that's equivalent. Then you compute your normal component of acceleration, take the derivative of this with the chain rule again. There's your normal component of the acceleration. And you can see that the normal component looks very similar to the acceleration, except for the 8. All right? So that means that the acceleration is pointing, it's a scalar multiple of the normal vector. Okay? And you can then compute t and n, you can compute a sub t and a sub n, and if you compute a sub n by this dot product and divided by the velocity, the speed squared, the curvature of that thing is a constant, 8 over 17. Okay, so it's a curve that's constantly bending. It has the same bend from point to point, which is what a helix will do. Okay. There's a helix. Every point along there, no matter what time you're at, it has the same amount of bend to it. It's not like that Fresnel spiral where the spiral gets tighter and tighter the farther you move along. Here it's just like we've got a coiled circle and it's bending at the same 8 over 17. That's how much it's bent by at every point. So if you move the point from here, right, it's the same as if it were bent here. So what you're saying is that this helix is made up of a wire that's been bent by a constantly bent at the same rate. Okay, so there would be an example of the computations worked out for this curve. You can find t and then the curvature, and if you go to the Mathematica demos on our website, you can see, t and plot, let's go to the frame. Here you go. You can see all your computations checked out for you. Okay, and yeah, and you can play around with these curves if you wish. Alright, so that's all that example is. I'll let you continue to work on the problems from the homework.